Hi, I'm Kathy Levinger. In this section we're going to look at relations and functions. Let's start with the definitions of those two. A relation is a rule that operates on one set, represented by the independent variable, and gives values in a second set, represented by the dependent variable. Another way to think of a relation is to think of it as a set of ordered pairs of independent variables paired with dependent variables. Our second definition here is a definition of a special kind of relation, a relation called a function. A function is a relation in which for each value of the independent variable there is assigned one and only one value of the dependent variable. So still a function is a set of ordered pairs of independent and dependent variables, but for each independent there can be one and only one dependent variable. Well, let's look at some examples of these in order to understand the definition. For each relation given below, identify the independent and dependent variables. So all of these are relations. Then we're going to determine if the particular relation represents a function. The first relation we see is given in words. It says, a computer purchased new for $3,000 decreases in value 12% each year. The value of the computer is related to the number of years since it was purchased. So our relation is between the value of the computer and the number of years. I would say the value depends on the number of years since purchased. So the value is the dependent variable. The value is the dependent variable, and the number of years is the independent variable. In this particular case. Well, let's look at our second example. Oh, actually, we should go back to the first and decide if our relation represents a function. In order to represent a function, we would need to have one and only one value for each year since the computer was purchased. Well, that can only be the case in any particular year. The computer is going to have only one value, and so we would call this a function. Well, here's a second example. In this case, I'll explain some of the conventions that you'll see in your textbook. We see a table of ordered pairs. The first row in the table are a set of x values. They're the numbers -2, -1, 0, 1, 2, and 2, 3, and 4. The second row in the table are a set of y values. They're the values 6, 7, 8, 9, 10, 11, and 12. The convention you'll see in your book is that the top row of the table, the x's in this problem, are the set of independent variable values, and the second row of the table, the y's in this problem, are the dependent variable values. So we've identified those. Now we need to decide if this set of independent and dependent variable values represents a function. It is a function if each independent value corresponds to one and only one dependent value. And you'll notice that that's true for the set of values. So it is a function. Well, let's look at our second set of ordered pairs, or our third relation here. The independent variable values are represented by the top row, or m, the variable m, and the dependent variables are represented by the bottom row, or the variable n. So we've identified those. In order to determine if this is a function, we want to be able to say that each independent variable only corresponds to one dependent variable. However, notice that -2 corresponds to 6, and -2 also corresponds to 10. There's a repeat with -1 corresponding to 7, and -1 corresponding to 9. For both of those reasons, this is not a function. Somewhere there is an independent variable value that has more than one dependent variable value to which it corresponds. Well, let's continue with this discussion by defining something called domain and range. The domain of a function is the set of independent variable values, sometimes called inputs, that make sense for the function. The range of a function is the set of dependent variable values, sometimes called outputs, obtained by applying the rule for the relation, to the values in the domain. Well, let's try this definition out with a couple of examples. Here we want to determine whether a relation given is a function, and it's given in table form, and we're also going to state the domain and range. The independent variable values are represented by the letter P, and they are 5, 3, 2, -1, 8, and 12. The dependent variable values are represented by the letter Q. They are 6, 7, 5, 4, 7, 0. In order to be a function, we need each independent variable value to correspond to one and only one dependent variable value. That's true in this example, so this is a function. Now we want to state the domain and range. I'm going to use capital D for domain and write that the domain is the set of independent variable values, and I'll list them in order from smallest, -1, 2, 3, 5, 8, 12 to largest. So there's our domain. To state the range, I'll use a capital R for the range, and I'll list the dependent variable values from smallest to largest. It's not necessary to list the value 7 more than once. So we'll list 0, 4, 5, 6, and 7 for the range. Let's try this again with a function, or excuse me, a relation given in a slightly different form. Here we have a relation that's given as a graph in an XY coordinate system, or a rectangular coordinate system. The graph contains this point and curves down and up and down and contains this point. We want to determine if this relation is a function. When you see a graph in a coordinate system, think of the horizontal axis as the independent variable values and the vertical axis as the dependent variable values. And so to determine if our particular relation is a function, we need for each independent variable value one and only one dependent variable value. So let's arbitrarily kind of stop at a dependent variable value somewhere in here, an independent variable value. The corresponding dependent variable value is on my graph right there. And if I go over here, there's an independent variable value and the corresponding dependent variable value is there. And I can continue that procedure over and over, and I'll see that for each independent variable value, there's exactly one dependent variable value, which means that this particular relation is a function. And this idea of looking vertically at a graph is something called the vertical line test for a function. The vertical line test says if a vertical line touches a graph only once for each of the independent variable values, then the graph is a function. Let's look at one more example. This time we're going to look at a relation given in words, and based on the description of the relation given, we're going to decide whether the relation is a function. So we need to take that information out of the verbal description. If it is a function, we're going to identify the independent and dependent variables. So here's our relation. On Sunday, Tim rode 110 miles on his bike. On Tuesday, he rode 55 miles. On Wednesday, he rested. And on Thursday, he rode 110 miles. Is the day he rode a function of the number of miles he rode? The way this final question is worded, we want day to be a function of miles, or we want day to depend on miles. So we would like the number of miles to be the independent variable value. And what I'm going to do is draw a table and fill in my table the information given in the problem. So I'm going to put number of miles along the top because it's independent, and the day is dependent on the number of miles. And so let's start with Sunday being day 1. He rode 110 miles. On Tuesday, day 2, he rode 55 miles. On Wednesday, he didn't ride at all, 0 miles. And on Thursday, the 4th day, he rode 110 miles. Now that my information is displayed in a table, I can see that the particular independent variable value 110 has 2 dependent variable values that correspond to it. So this relation, as I've designed it, is not a function. Well, in this lesson we've looked at relations and functions. Be sure to work lots of exercises from your book to practice this.